And now, please welcome to the stage Hayata Yamasaki.
Thank you all for coming to this session. I am Hayata Yamasaki from University of Tokyo. I'm chairing this session. It is a pleasure to introduce our invited speaker, Ben Reichardt, who has made significant contributions to the field of fault-tolerant quantum computation over the years. Today, he will be presenting his recent collaborative work with Microsoft and Atom Computing on fault-tolerant quantum computation with a neutral atom processor. Please join me to welcome the speaker.
Thank you. I'd like to thank you for the opportunity to speak here. And I'd also like to thank my co-authors, Adam Peitznick, David Asen, Ivan Basov, Juan Bello-Rivas, Parsa Bonderson, Rui Chao, Wim Van Dam. Whew. So I think about maybe a third of us are from Microsoft and maybe 2/3 of us from Atom Computing. But it's a collaboration between the two companies. So let me begin with a very brief and incomplete and superficial summary of the state of a few of the commercial quantum processors out there today. So we have superconducting qubits, trapped ion qubits, and neutral atom qubits. Superconducting qubits, of course, exemplified by IBM and Google systems, have around 100 to 150 qubits. Perhaps their main advantage is their speed. They're very, very fast. I think Google's papers have millions of shots, so lots of data they're able to take. The error rates are in the range of 3 to 4 times 10 to the minus 3 per 2-qubit gate, although different gates have different error rates. So some of the gates are going to be considerably noisier than others. Trapped ions, on the other hand, are slower. Neutral atoms are slower. Neutral atoms have the advantage of bringing us much higher scale. So Atom Computing's last device had 256 qubits, a 16 by 16 array of qubits, which is considerably larger than any of the other devices out there. Trapped ions have the lowest noise rates right now, maybe just 1 times 10 to the minus 3 error per 2-qubit gate. Another factor that's important between these devices is the connectivity. So the superconducting qubits are these solid-state qubits. They're arranged on a 2D plane. And IBM system, the connectivity, the degree of the qubits is 2 or 3. And Google's system, they're degree 4. They form a planar grid. But it's very limited connectivity, and this limits the applications. It makes it harder to do very, very many things. Whereas trapped ions and neutral atoms, they're very flexible because they have what's called sort of advertised as full connectivity. And indeed, any qubit can talk to any other qubit. You can have gates between any pair of qubits, which is very nice. On the other hand, the way you achieve this full connectivity is by moving the qubits, the atoms, next to each other. And by moving them next to each other to achieve this full connectivity, that's sort of what slows these machines down. And so you're obtaining high flexibility, but the trade-off for that is it's slowing the computations down. So what's the problem we're trying to solve? So errors are basically the main problem when it comes to building a quantum computer, especially a large quantum computer. All of our devices right now have error rates, as we saw on the previous slide. The best devices have error rates on the range of 10 to the minus 3 to 10 to the minus 2, 1% per operation, per 2-qubit gate. And for applications, optimistically, there are applications with error rates maybe 10 to the minus 6 per operation. But for a lot of applications, we want error rates even smaller than that, 10 to the minus 8 to 10 to the minus 12 error per basic operation. And the way we're going to get here is not by better engineering. We're not going to engineer our devices to be 9 orders of magnitude more accurate. Instead, what we're going to do is we're going to use quantum error correcting codes. So we're going to take a collection of physical qubits, put them in some interesting entangled state, a quantum, a code word, and it'll represent one or a few logical qubits. And even though the physical error rate will still be in the range of maybe 10 to the minus 3, if we're lucky, 10 to the minus 4, the logical error rate will be in this much lower range. And so right now, this transition of running circuits at the logical level, instead of just running circuits on bare, unencoded qubits, is sort of where the field is in terms of demonstrations of quantum computers. So that's what I'd like to talk about. And in particular, we've seen a couple of different classes of experiments recently. One is just memory for logical qubits, and two is running computations on logical qubits. Memory is just repeated error correction, so it's not super exciting. You run error correction, then you run error correction again and again and again and again. And in fact, often it's even more boring because error correction itself consists of just like multiple cycles of syndrome extraction. So you're just extracting the syndromes over and over again. And you could ask, what's the point? Well, I'll get to that in a second. But it is interesting. And there's been a lot of really interesting results on memory recently. In particular, a nice one has come from the Google collaboration. So here they use the surface code. So the surface code that they used took 101 physical qubits to represent one logical qubit. And they demonstrated that per round of error correction, the error rate on the logical qubit was 1%. This is interesting because it is actually less than the physical error rate. So the logical qubit is better protected than the physical qubit, which is quite nice. Microsoft, working with Quantinuum, introduced the carbon code. The carbon code uses 15.5 physical qubits to represent one logical qubit. And the error rate was around half that, so 0.4% per round of error correction. Then we introduced a slightly more efficient code, the tesseract code. The tesseract code uses 4.5 physical qubits to represent one logical qubit. And the error rate per round of error correction was around 1/50th of a percent, 0.02%. And so using more efficient codes, you're able to, well, with less overhead, you can store your logical qubits and actually have less error on your logical data. So one moral from the slide is that actually the code matters a lot. When you have the freedom to choose different codes, it's worth it. And there's a lot of room for innovation in code still. So not just at the scale of very large, asymptotically large codes like LDPC codes, which are of course extremely interesting theoretically and possibly practically in the future, but in the range of these smaller codes, I think there's a lot of room for innovation. And additionally, the reason we're able to use that innovation is because of the flexibility, the full connectivity of the trapped ion and neutral atom qubit devices. They allow us to experiment with these different codes that require higher connectivity than just the surface code. Now let me put a couple of asterisks on this slide. One is, this is of course not comparing apples to apples. So these experiments are being run on different devices, superconducting qubits, different technologies versus ion traps. And even the two results at the bottom on Quantinuum's ion trap system, they're on different versions of the system. It's been upgraded between those experiments, and it's been upgraded since those experiments further. So the devices are always getting better. And another caveat I'd like to put on this is that so Google's experiment there uses a distance 7 surface code. The carbon code and the tesseract code have distance 4. So in particular, having even distance means that there's some modest amount of post-selection going on. And that's fine. It's certainly allowable to use post-selection, and it's appropriate to use post-selection. It's scalable in theory, but at the state of where the machines are right now, this is about the right amount of post-selection to be using. right, but let me emphasize again the advantage that full connectivity gives us versus just using, say, grid connectivity with the surface code. So for comparable protection, you could use the surface code with distance 4, which with the standard embedding uses 31 qubits, 16 data qubits, and 15, if I have it right, ancilla qubits, to represent one logical qubit. The tesseract code, on the other hand, uses 18 physical qubits to represent 4 logical qubits. So it's about 6 times more efficient in terms of qubit overhead per logical qubit. The number of gates is about 1/3 the number of gates per round of error correction. So again, when you have higher connectivity, you're able to use much more efficient codes, and this is quite beneficial. All right, so why is this memory experiment, repeated error correction, why is that an interesting experiment to run? And the reason is basically because it's a fundamental primitive in fault-tolerant computation. So here I've drawn a cartoon that shows very roughly the error level or the noise level in your quantum computer plotted versus time or steps of calculation. So you can think of the error level starts off at some small amount, and as you run the calculation forward, the error level is going to increase and increase and increase. And for short calculations or simple calculations, you can stop the calculation, measure the data, and decode it in your classical computer, provided the error isn't too large. But for any longer calculations or calculations that are more complicated, you're going to have to run error correction periodically. And here, this is a cartoon. Again, you can sort of see the error building up. You run error correction. The error builds up when you do a few more steps of computation. You run error correction again. And notice, the error level never drops to 0 because error correction itself has errors in it. So it's fault-tolerant error correction, meaning it's allowed to have errors, and it still works, but it's not perfect error correction. And really, actually, this cartoon is a little bit misleading too, because in some schemes, like the surface code or like the tesseract code, error correction is happening all the time. So you don't even have this dichotomy between computation and error correction. But still, whatever. It's not that bad. The point of this is just to say that repeated error correction is a real primitive that you're going to have to run all the time in computation. And so it's extremely important to get repeated error correction down, working well. And it's not because we want to store logical quantum data in superconducting qubits, because that superconducting qubits are not a good memory. The reason for running error correction on superconducting qubits is to run, ultimately, to run computations. All right, so we've now run the first encoded quantum computation that requires fault-tolerant error correction and that benefits from fault-tolerant error correction. Here's the logical circuit at the left. It uses 8 logical qubits with 3 rounds of transversal control NOT gates. And what it generates is the graph state corresponding to the cube. This is the physical circuit. You can see that the 3 rounds of logical transversal C0 gates are implemented by 3 rounds of physical transversal C0 gates. But this is again using the tesseract code. So 2 blocks of 16 qubits representing 2 blocks of 4 logical qubits. And you can see the problem here. The problem here is that if there's a single fault on the input, it can be copied down into 3 faults. If there's a single fault on the top block on the input, it can be copied down onto 3 faults on the second block. So a single fault can actually cause a logical error. This is not fault tolerant. The way to make it fault tolerant is we have to insert error correction. And so by running error correction between the logical gates, you catch this kind of the kind of bad fault that's on the right, and you prevent errors from spreading poorly. And so indeed, we run this and it works, and we show, for example, that if you run the physical circuit just using 8 bare unencoded qubits, the error rate was 2.3%. when you run the encoded circuit using 32 physical qubits plus 4 for error correction, so 36 qubits total, the encoded error rate was 0.2%, so 10 or 11 times less than the physical error rate. It does work. Still, we'd like to run computations on more than just 8 logical qubits. And so that's what I'd like to get into in the second part of this talk, is how do we do computations with hopefully many logical qubits. And this is a collaboration between Microsoft and Atom Computing. Atom Computing is building a neutral atom processor, and we're working with them to develop codes and to develop applications to run on this processor. And so quantum computers based on neutral atoms potentially offer many, 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 many qubits, very large scale. So here are a couple of references from last year. The top one is a result from Atom, where they have a 1225 site array, and and I think it's 99% filled with atoms, with qubits. So you have well over 1,000 qubits here in this array. The bottom picture shows a 12,000 site array, which has 6,100 qubits, 6,100 atoms in it. So it's about 50% filled. And so you can see that we can achieve potentially lots and lots of qubits with these neutral atom systems. Of course, we've heard this story before. So D-Wave in 2019, for example, announced a 5,000 qubit superconducting qubit quantum computer, quantum computing device, whatever you want to call it. And I think last year D-Wave announced that they have a 4,000 qubit, but less noisy quantum computing device. So what's different with neutral atoms? A big difference is we're talking about the circuit model. It's not an analog model of computation. We're not using adiabatic optimization, something like that. We're using the digital circuit model. And as I said, it's completely flexible. You've all-to-all connectivity by moving atoms around and stuff like that. We have high qubit lifetimes, high fidelity 2-qubit gates. So this is a slide from Mark Safman where he's plotted the fidelity of the 2-qubit gate over time. And you can see back in 2020, the fidelity was, well, 2020, maybe it's 90. I don't know, if you go back to 2019 or so, it looks like the fidelity is maybe 90%, then it increases up to 99%, and now last year there's a result from Caltech where they have 99.7% fidelity 2-qubit gates. So that's 3 times 10 to the minus 3 error, which is similar to superconducting qubits, maybe slightly better than superconducting qubits from a few slides back. And also that's interesting here is the trend line. So if the trend continues, which is a big if, of course, but if it does continue, then hopefully we'll be able to get even lower noise rates for these 2-qubit gates. Okay, so this is another slide that I've stolen. This is from Atom, and I don't understand it. I think this is supposed to give you an overview of the device. So you have like a chamber at the top where the atoms sit in this 2-dimensional array. They're trapped there with lasers. And at the bottom, you have atoms coming in, and they're cooled down, and they're loaded slowly into the array, and stuff happens, and lasers are shot at them and stuff. One thing that's interesting is this picture at lower right. So it shows you the coherence time of individual qubits. And so it looks like they can measure a coherence time of like at least 30 seconds. I think this is a pretty old result. I don't know if it gets any better, or if it's gotten any better since. So pretty long coherence times. They're pretty good qubits for memory. Let me try to show you, instead of focusing on the physics, let me try to show you what it's like to use this machine as someone like me, as a user. What do we do with this machine? How does it work? And so to start with, as I said, it's a 16 by 16 array of atoms of qubits. Interestingly, you don't actually get all the qubits necessarily all the time. So here you can see there's a couple of holes where a qubit's missing, an atom's missing. And that's because sometimes you haven't loaded all the qubits. So typically the load failure rate is less than 1%. So if you have 256 qubits, maybe 1 or 2 or 3 atoms might be missing, or none. Maybe you get all 256. It just depends. Let's see. So at the bottom, there's a couple of extra rows, or a few extra rows. That's called a reservoir. And this reservoir is used to fill in holes of lost atoms during the circuit. As a user, you don't have to worry about the reservoir. That happens automatically. There's these highways. So the atoms are not packed together as closely as possible, like you saw on the previous slide, a couple slides back, because you need room for the atoms to move around. And so you have these highways. I think this is not to scale. I think the highways are wide enough for 2 atoms to move from side to side. What else? So 1 qubit gates can be applied in parallel to a row, to any subset of qubits in a row. The lasers come down from the top, I think. And so you can do Z rotations, which are basically perfect because it's just a timing issue, or you can do X rotations. X rotations are, they're all very fast. That's not the issue. They're fairly high fidelity. So 1.5 times 10⁻³ I think at times they've benchmark error rates on the order of 10⁻⁴, but probably 1 or 2 times 10⁻³ is more typical. To get to the 2 qubit gates, we have an area at the top, I think it's the top, called the interaction zone. What you can do is you can move qubits up and down into the interaction zone. And so you can take 1 or 2 qubits from the same row. They have to be in the same row, and you can move them up to the interaction zone. Anywhere in the interaction zone that you want, you can put them. Just the important thing is they can't cross each other. So if you want them to cross each other, you have to do it in 2 separate movements, 1 at a time. And actually, you can move more than 2 qubits. You can move up to 8 qubits at a time, but then you have more constraints. And actually, in all of our experiments, we're only using 2 qubits moving at a time. The time it takes to move is about 1 millisecond. I think it's similar no matter what row you're moving to the top. So from the very bottom to the top, I think is around 1 millisecond too. Something like that. And this is actually the key thing, right? That's pretty slow. This is the bottleneck that limits the speed of the device. So 2 millisecond round trip time from the interaction zone. In the interaction zone, it's 16 across, and so there's 8 pairs. And so you can do 8 controlled Z gates. Controlled Z gate is a natural gate in parallel. Up to 8. You don't have to do 8 if you don't want to, but that's the limit. And the time it takes to apply a controlled Z gate is about 0.2 milliseconds. And so this is not the bottleneck, right? So the round trip movement time is like 2 milliseconds, and so CZ gates are about 1/10 that. The speed isn't that important. And the error rate, this is the limiting factor. The error rate is around 6 times 10⁻³ plus you have an additional 0.3% loss. So what do I mean by loss? I mean that one or both of the atoms is gone. It's not trapped anymore. And that's sort of an overview of the device. And I say the current device, and that's unfortunately not true. This is the current device as of December or so. The device is being upgraded constantly. But hopefully this gives you a flavor of how the device works, and at least how it's worked very recently. Yeah. So what is it like to use this device? Well, so here's a circuit on the left. The circuit on the left prepares a cat state, a 24-qubit cat state. Just by you see that the qubit at top left is ket plus, and every other qubit is ket 0, and you slowly spread entanglement down. So what you do is you compile it into the architecture. So you have to schedule all of the 2-qubit gates to happen in the interaction zone. And so the picture at right shows one schedule for this gate. And here I've zoomed in a little bit so you can see it slightly better. So notice, for example, that the first qubit goes up and it sits in the interaction zone the whole time because it's being used in a controlled Z gate in every single step. That's fine. You don't have to go up and down if you don't want to. You can just leave the qubit in the interaction zone. Another thing, like the second qubit does a Hadamard, it goes to the interaction zone, you apply the CZ, and then it goes back down to apply a Hadamard. And so this is because, so conjugating the Hadamards by the CZ will give you that controlled NOT gate. And another thing to notice here is that the 1-qubit gates can only be applied down on the register. The 1-qubit gates are not being applied in the interaction zone. So you have to move that second qubit back down into the register to apply that second Hadamard gate. And actually, I guess I should have said this before, every qubit has a home location. So basically, you can move a qubit from its location in the register anywhere in the interaction zone, but then you have to move it back to its original location in the register. And the reason for that is because 1-qubit gates are calibrated for the location, for its home location. So you kind of have to move it back to where you started and not just to an arbitrary place in the register. All right, and what else can I say about this? I don't know, like one sort of trivial observation here, like if you look at qubit 3, the Hadamard gate on qubit 3, it's kind of delayed until as long as possible. And that's sort of to minimize the dephasing window, to minimize the amount of time that you're in Ket plus, so you're not subject to dephasing unnecessarily. I don't know if that makes any difference, but you might as well make small optimizations like that, since it's easy. All right, so this overall is a schedule for preparing a 24-qubit cat state. Let's dig into, again, what it looks like when you run this in an experiment. So first of all, they load all the atoms. Hopefully they get all 256. Maybe they'll only get 255 or whatever. You apply the circuit. At the end of the day, you're going to measure everything. And their measurement has 2 steps. First, they image every qubit that's in the Ket 1 state, in the 1 state. Then they pump zeros into ones, and they image every qubit that's either a 0 or 1. And that's it. So basically, these 2 measurements let you say which qubit is a 1, which qubit is a 0. So a 0 will light up in the second picture, but not in the first picture, and which qubits are missing. So if a qubit is missing, you'll see a black spot in both images. This ability to image loss, I think it's different from like the Harvard machine or the Quera machine. I don't think they're imaging loss. I could be wrong. But it's a really nice feature of this device. And then every few trials, they reload all the atoms because some of the atoms are being lost. So just notice a couple of things that are not here. These are features that are being added right now, are mid-circuit measurements. So right now, in these experiments that I'm talking about, all the experiments are being done, all the measurements are being done at the very end, not in the middle. Reloading is happening only between experiments and not during an experiment. And in these experiments, there's also no adaptive control so far. So you can't say, I don't know, inject a magic state and do a measurement and controlled on the results, change the circuit that you're applying so far. These are all going to come, of course. So what do we get back at the end of the day? Well, what we're going to get back are a bunch of bit strings. So here, for example, this is again for the 24-qubit cat state. You might measure the all 1 string. That's good. That's a nice answer. You might measure the all 0 string. That's good. In this third string, it looks like there's an error on qubit 7, and it's propagated or it's happened simultaneous to an error on qubit 23. You know, that's bad, but it happens, of course. In this fourth string, You see there's a dot, and the dot means that the qubit is lost. It's not a 0 or a 1. And not only that, but you can see that when it was lost, so it was actually missing before the circuit even began. So you had a load failure. One of the 24 qubits wasn't present when you started running the circuit. That can happen. In this row, there's an X. And the X means that the circuit was present initially, but it was lost by the end. So we're going to call that a circuit loss. The atom's gone missing during the computation. In this string, you have both a dot and an X. And it's interesting here. You can see, for example, the dot, the lost qubit, the initial loss, has spread to an error on qubit 12. So qubit 12 should be 1, and it's a 0. And it's also spread to qubit 20. It's propagated into an X error on qubit 20. So here, like, we can diagnose the reason for why qubit 20 is a 0. It's because qubit 4 was lost. I mean, that's the most likely explanation. Or, yeah, that's the explanation, almost certainly. So what we can do at the physical level is we can just discard these shots. So if you have a shot that some of the qubits are missing, we'll throw it away and run it again. And this is a nice feature. It lets you filter out just the good data and keep the good preparations. And this is possible because, again, because we can image the losses. At the logical level, when we start to run logical circuits, we're going to try to correct for losses and not just throw away those shots and try to come up with a more scalable approach. So here's the data for the unencoded cat state. On the x-axis is the size of the cat state. On the y-axis is the fidelity. You can see, for example, that they can prepare a 40-qubit cat state with 62% fidelity. And that's counting only those trials in which there is no load loss and no circuit loss. So all 40 atoms are present at the end of the final measurement. And that was about 46% of the trials. So in 54% of the trials, at least one atom was lost. And so they throw those away. You can also look at the data like if you pretend like you didn't have the ability to image loss, so you could say replace every lost qubit with the maximally mixed state, say, and estimate what the fidelity would be, and you get these lower numbers but with higher acceptance rates. So the black points here include all data, including runs with loss, and the gray points include all those data points in which there was no initial loss. So all the qubits were present when you started the circuit. So this is a nice plot due to Mario Kren that shows the largest physical cat states prepared over time, and the different colors give you the platform, the technology that was used. So for example, blue is trapped ions, and the last two data points I think are from Quantinuum. They prepared a 32-qubit cat state on their, I guess, yeah, their H2 system. Orange is neutral atoms, and so they've now prepared a 40-qubit cat state. We've now prepared a 40-qubit cat state. Purple is superconducting qubits, so there's a sort of a special purpose computer or device that's prepared a 60-qubit cat state. And that's kind of where the status is right now. Still, we'd like to do more interesting things. We'd like to do encoded computations. That's what I started about talking about. So let me shift to that. And let me try to talk about how we do encoded computations using all 256 atoms of the device, not just, say, 40 atoms, 40 qubits. So here's a circuit that prepares, so you see there's two parts to the circuit. The top part, well, they're the same. Two copies of the same half circuit. Each of these prepares, I guess, logical plus encoded in the 832 code. It's a color code on the cube. If you put these together, you get logical plus 0 encoded in the 16-qubit tesseract code. So what we're going to do is we're going to fill up the 16 by 16 array of atoms with copies of this 8-qubit circuit, just running it over and over again. So in every column, I'm going to have 2 copies of this circuit running, and then 16 copies going across. And they're paired up, as you can see here. Two columns next to each other are paired up. And the reason for this is basically those 2 copies are going to run in parallel. So whenever you need to move an atom up into the interaction zone, you're going to do the exact same movement with its partner column. So both of these columns are going to be running at the same time, both of these circuits running at the same time. Okay. And here are some of the results. So running this, we have, let's see, so we have 1, 2, 3, 4, I don't know. It looks like we have 32 copies of the 8-qubit circuit. I think that's right, yeah? Sorry, I can't do math. 32 copies of the 8-qubit circuit or 16 copies of the 16-qubit circuit. So we're preparing up to 16 code blocks of the tesseract code. And here what I'm plotting is a histogram for the number of code blocks that are correct, that have no logical error when you measure and decode. So on average, it looks like you get around 11 code blocks correct, which, you know, if you're a marketing guy, you could say that means I have 11 code blocks. Each code block has 6 logical qubits, so that's 66 logical qubits. That's not right at all, because, really you have 16 code blocks, so you have 96 logical qubits. The problem is a lot of them are faulty. A lot of them have logical errors, and you don't know which ones have logical errors or not. So the fact that you have 66 out of 96 and you don't know which 66 are good doesn't make it very useful for much. But it's a start. It's a start to try to use the whole machine and start to create entangled states across the whole machine. Here I've run this similar circuit. This is now a fault-tolerant circuit for preparing the 832 logical +++ code word. And this circuit uses 10 qubits, so 8 physical qubits to prepare the state, and then 2 more qubits to verify 2 of the stabilizers to make it fault-tolerant. And so now what I've done is I've grouped the blocks of this device into the qubits in this device into groups of 10 qubits and pairs of 10 qubits. So in the boxes there are pairs of 20 qubits. And again, those sets of 20 qubits, each of them can be used to prepare 1 tesseract code word. And you can see in red is the, again, a histogram for the number of correct blocks. And it's significantly lower. Now it looks like on average you get around 4 good logical code words with which you can start a logical computation. But the advantage now is that you essentially know which code words are good and which code words are bad because of the flags, because of the verification that you do. So the fault-tolerant circuit, yeah, it's true you get many fewer logical qubits, but they're now much more useful. And indeed, the logical error rate is almost 10 times less, 8 times less maybe. So it's significantly better. All right, still, we like to run computations, not just initialized states. What kinds of computations can we run? Well, an interesting feature of this device, which comes down to the physics, is that the gates are designed so that a lot of the 2-qubit error is converted to atom loss. And you can think of this as actually a feature of the device because they have the ability to detect, to image, to measure atom loss. And atom loss is a really nice error model, right? Because when an atom is lost, you know that it's lost, and it makes it a lot easier to correct that error. Sort of roughly intuitively, a lost atom is like half of an error, or one error is like 2 losses, roughly. In particular, there's a really nice code, the 422 code, that encodes 2 logical qubits into 4 physical qubits. And this code has a property, it can detect any one error, If you detect an error, you have to throw it away and start over. But also this ability that you can correct any one loss. So if one of these 4 atoms is lost, you can replace it, and the data qubits are not modified. So we can protect against atom loss using very efficient, very small codes. And indeed, that's what we do to start. So we're preparing a 24-qubit encoded cat state using the 422 code. And here I'm plotting on the same scale as the unencoded cat states. That's a little bit misleading because encoded cat states are completely different things from unencoded cat states. In particular, hopefully they have significantly lower noise rates. Here, let me zoom in on the orange box. So this is encoded history of experiments for preparing encoded cat states, and it's all from 2024. So neutral atoms is in orange, superconducting qubits in blue. These results are not exactly comparable to each other because they're using different codes. So we're using the 422 code. Before we were using the tesseract code. We had 12 logical qubits. Harvard used the 713 Steen code. So why are these different? In particular, I mean, they're obviously different, but one reason they're different, for example, is in the 422 code, we have 24 logical qubits distributed among 12 code blocks. In the tesseract code, we have 12 logical qubits distributed between just 3 code blocks. So it's a very different entanglement structure, actually, even though they're both encoded cat states. A second thing that's different between these results is the error rates are different. So the error rates range from, for our result, they range from 10% to 27%. For the tesseract code, it is around 0.2%. Different error rates for these different results. What does the circuit actually look like? So let me walk you through that. So the circuit on the left is a physical circuit, it's a logical circuit that we're going to apply on 24 logical qubits. And the qubits are divided into pairs. So there's 12 pairs of 2 qubits, and those pairs, we're going to encode each pair into one block of 4 qubits, one block of the code. As you can see on the right, so on the right, and here I've zoomed in a little bit, you can see there's, 12 blocks of 4 qubits. I think that's right. And they're initialized, and then you do sort of transversal controlled Z or controlled NOT gates between them to spread the entanglement around. And you can see here, like the first code block is preparing logical plus 0. And logical plus 0 for the 422 code is just 2 bell pairs. So we're just starting with 2 bell pairs. That's fault tolerant. The second code block and all the subsequent code blocks are prepared in logical 0, 0. Which is actually a cat state, or maybe a dual cat state. And so this little 5-qubit circuit is what's being used to prepare a cat state fault tolerantly. And the 5th qubit is used to verify that nothing bad has happened. So pre-selection or post-selecting, you should measure that qubit to be ket 0. So the compiled circuit overall has 59 physical qubits. So there's 12 code blocks of 4 plus 11 ancilla qubits, the gray qubits, and it has 101 physical controlled Z gates. So it's a fair number of controlled Z gates. Okay, then you have to schedule it on the actual device, but before you schedule it, you have to decide like which atoms go where, right? Because you have to place the atoms in the device. And here, what I'm going to do, maybe you could do something fancier. I'll just do the natural thing. So I'll have 4, each row has 16 qubits across, so I'll put 4 copies of the 422 code in each row. And I spread them out like this, so the pink qubits are sort of alternating with the green qubits and the purple alternating with the blue. I think I did that because I was trying to use the 8 parallel moves, but at the end of the day, we didn't actually use those, so be it. It doesn't matter. And then scheduling the gates, this is what the schedule looks like, including movements. You can sort of see 2 qubits moving at a time. Some qubits are spending a lot of time in the interaction zone, others aren't. That's kind of what it looks like. This is some of our results. So on the left is the unencoded qubit. It shows the error rate in the x basis. So when you measure a cat state in the x basis, you should measure just a random string of ones and zeros that has even parity. And when you measure in the z basis, you should measure either the all zero string or the all one string. Anything else is an error. And so here I'm plotting the x error, the z error, and the sum of their errors in the middle. For the baseline unencoded, the sum of the error rates is 42%, and the acceptance rate is 37%, meaning that in 37% of the runs, you had no loss at all. So I'm throwing away all the trials that have any loss. And then the encoded results, like the middle column, shows you that the total error rate is 26.6, about 27%, using the 422 code. And the acceptance rate was about 5.9%. So you have a lower acceptance rate, but you also have a lower error rate. So you're trading off, you're trading that off. But it is working. So error correction, loss correction is working. You're able to reduce the error rate, get a more accurate cat state or encoded cat state using this code. The column at the far right is where I'm discarding any trial that has any error or any loss, any detected error or any loss. So the acceptance rate goes way down, but the error rate also goes pretty far down. Interestingly, it looks like the z error rate goes down a lot more than the x error rate. I forget why that is, but that seems interesting to me now. Here's more detail on the data. I think this was taken like October 30th last year, so overnight on October 30th. I think it's like, I don't know, it's maybe 60 different runs. Each data point is one run, and these data points are taken like just sequentially, I guess. And each run has 300 shots of the encoded cat state. Blue is x basis measurement, red is z basis measurement. Yeah. To me, this is an interesting plot because it suggests to me that some of the runs are better than others. Like if you look at the runs and sort of in the bottom right, those look really good. So it's like maybe the machine is better sometimes than other times. You know, they're automatically calibrating the machine all the time. But even still, it looks like sometimes the machine might have lower error rates than other times because when the acceptance probability is high, like 18%, the error rate is lower. I don't know. It's not proof or anything, but to me that's suggestive, this kind of correlation. And of course, we'd like it if all the time the machine were acting at the optimum parameters. Some more details, some more statistics as well, and like how often are we actually correcting losses? Is loss correction actually happening? In fact, it is. So the load loss was about 1% in this experiment, a bit higher than we'd like, but so be it. In correct trials, on average, there were 1.8 atoms that were lost. So that's out of 59 qubits total, but if one of the 11 ancillas was lost, you discard that trial. So that means 1.8 out of 48 qubits were lost. It's a fairly high loss rate, but the code, the 422 code, is still able to correct for that loss rate, and you're still able to decode correctly. So it still works. On bad trials that decode incorrectly, the average is 2.6 circuit losses per shot. And so this suggests that actually one way of distinguishing between good and bad trials might be to threshold based on the number of losses. And indeed, you can do that. So you can select only those data points that have at most, say, 2 losses and see what happens. That's what I plotted on the left. You can see, for example, if you select on only those runs that have 2 or fewer losses, the acceptance probability goes down a bit, not too much. The error rate goes down a bit too, well, fairly considerably. So it's actually a really nice error model. This loss error model is really nice to work with because you get a lot of information about what's happening inside the machine, which you don't get with a standard error model. Like with the bit flip error, you don't know where the bit flip error happened or anything. With losses, you know exactly what happened, or pretty much what happened. Yeah. All right, so second I'd like to talk about the Bernstein-Vazirani problem. So here we'd like to not just create a cat state, create an interesting entangled state, but we'd like to run an interesting entangled encoded computation. And the simplest computation to run is the Bernstein-Vazirani algorithm. So the goal, we all know this, there's a secret string in this oracle, and we'd like to find this secret string using as few queries as possible. Classically, if the secret string is length n, it takes n queries. Quantumly, we should be able to learn the secret string with just one query, just by transversal Hadamards after applying the oracle. The way we implement the oracle is with a bunch of control NOT gates. So x, the query to the oracle, is stored, the qubits of x, or the bits of x, are stored in the controls of these different control NOT gates. And whether the secret is 1 or 0 says whether or not you apply that control NOT gate. And so in particular, one thing you can see from this is the all 1 string. The secret with the all 1 string is sort of the hardest to implement in practice because it uses n C0 gates. The all 0 string would be extremely easy to implement because it has no C0 gates. All right, that gives you a flavor. What's been done before with the Bernstein-Vazirani? So this is sort of a Mario Kren style plot. You can see trapped ions and superconducting qubit implementations with different sizes of the secret, different values of n, plotted over time. So for example, in 2021, it looks like they implemented Bernstein-Vazirani with 20 qubits. This was on IonQ's device. But they implemented it with a random string, s, which means that it's roughly the same as like 1 to the 10, 0 to the 10. So basically it's hammering away 10. So you're basically applying 10 C0 gates. And they had a 70% success rate. In 2022, they implemented it on superconducting qubits. This is IBM's device. They had a 0.2% success rate on the all 1 string. And 0.2% doesn't sound so good, and it's maybe not so good. But on the other hand, if you want to be optimistic, classically, if you had 1 query to this oracle, your success probability would be 1 over 2 to the 25. So maybe 0.2% isn't that bad. We're implementing it with n equals 27. And I think it's a coincidence, basically, that it's 1 more than 26. It wasn't deliberate. But yeah, it is 1 more than 26. We implement it with n equals 27, both at the physical level, and we're the first to implement it at the encoded level. Again, we're going to use the 422 code. At the unencoded, so with just 27, this is for the all 1 string, so using 27 C0 gates. The unencoded algorithm had a 70% success rate. The encoded algorithm had an 81% success rate. So encoding the algorithm indeed was helpful. This is what the circuit looks like. It's quite simple. The logical circuit on the left is quite simple. It uses 28 qubits, 28 logical qubits, 27 logical C0 gates. The compiled circuit on the right looks like a mess. Yeah, it's a lot bigger. There's 112 physical qubits. So we're using about half the device. Uses 164 physical CZ gates. The depth is probably 28, just guessing. It looks like it's around 28, so it's a fairly deep circuit. Also notice we're using the all-to-all connectivity. That first code block is connected to all the other code blocks in the machine. And I think the way we're going to schedule this, let's see. Yeah, we're going to move that, we're going to initialize that first code block, and then we're going to leave that first code block in the interaction zone for the whole computation. I'm pretty sure. So those first 4 qubits are just left in the interaction zone, and then in every round they're doing transversal C0 gates into other blocks of qubits. And here, all of the loss correction and error detection is happening at the very end. We're not doing intermediate rounds of error correction. So this is what some of the data points look like. We see, for example, with n equals 27, the acceptance rate was, the error rate was maybe 20% for the encoded algorithm versus 30% for the unencoded algorithm. So the encoding helped. But on the other hand, you're trading off the acceptance rate. So the acceptance rate was only 9% versus 18%. the 422 code works. Maybe let me not go into too much detail on this. Well, here, let me say a little bit. Of course, this algorithm was initially, the Bernstein-Vazirani algorithm was initially envisioned as a quantum query algorithm. And in the quantum query where you're only allowed one query. So you can't reject and say, I detect an error, start over. That's cheating. I mean, if you think of it as a real quantum algorithm, then that's fine to get the answer. But if you think of it as a quantum query algorithm, it's a little bit of cheating. So you could also look at the performance of the algorithm based on a single query. And if you have a single query, you have to say, what do I do if I detect an error? Or what do I do if one of the atoms is lost? And so, I don't know. I mean, the best thing you can do in general is you can guess the secret string at those positions. So if you detect an atom was lost, your probability of guessing that bit of the secret string is 1/2, and the expected Hamming distance is going to increase by 1/2. And so using these two measures, expected Hamming distance and the probability of guessing the correct string, you can evaluate the encoded algorithm versus the unencoded algorithm. That's the middle and the right columns in this table. You can see in general, actually, it looks like the unencoded algorithm has a higher probability of guessing the secret string, modestly, but still slightly better, higher probability, whereas the encoded algorithm has a slightly lower Hamming distance from the encoded string. Again, very small, but slightly better. I think the reason for this is actually because the unencoded algorithm and the encoded algorithm have different sort of failure modes, which you can sort of see in these histograms. So in the unencoded algorithm, the most common error looks like sometimes you have up to 3 losses. Most of the time, you maybe have 0 losses or 1 lost atom. But more commonly, the failure rate is when you have an error in the middle of the string and you end up with a string like 1111000000. So an error happened in the middle somewhere. Whereas with the encoded algorithm, the most common error is actually, so the code converts errors into undecodable blocks. So if a block has an error, that code block is converted to basically a lost block, because you don't know what the block decodes to anymore. And so that has Hamming distance only 1/2, whereas the unencoded algorithm, when an error happens, you get Hamming distance 1. And I think that's sort of what's going on for why you get this different behavior. One could look into that in more detail. Here's a few other results. We run repeated loss correction and error detection for the first time with neutral atoms. The results aren't that great. You see some modest improvement over the baseline, but the error rates aren't extremely low. We run up to depth 10 logical circuits. We run actually error corrections. We test the distance 3 and distance 4 Bacon shortcodes, and the results aren't that good. But we did try it. So this work is based on a partnership between Microsoft and Atom Computing. Atom, they've built a 256-qubit quantum computer with the highest 2-qubit gate fidelity for any commercial neutral atom system. We've prepared this 24-qubit entangled cat state, and we've run the Bernstein-Vazirani algorithm at the logical level on up to 28 logical qubits. Here's the paper from November with our authors. Here are 2 other papers. The paper with Quantinium, I talked a little bit about this at the beginning, and maybe if you've seen the news, there's this paper about Majorana qubits. I obviously haven't talked anything about that. I'm told there'll be a talk. I think there'll be 3 talks at the APS March meeting. Here's one of them on March 18th, if you're interested in that. That's all. Thank you.
Thank you very much for the nice talk. Due to the time constraint, we may not have a question time now, but let's postpone all the questions and discussions in the lunchtime, and let's thank the speaker again.
Howdy, y'all. Just some quick housekeeping items. Microsoft will be hosting a industry lunch. Brown bag, please bring. to room 402 at 12:30. Also, there are QR codes all around the building to submit your items for this evening's rump session. It's a very quick web form. And lastly, lunch in the building is available at the cafe. Thank you.